So everyone, this is Russell Williams. Russell is 28 years
from in frequency assignment work from about mid-1970s. From there on, always frequency assignment work.
Right. Currently he's working for a company called
RadSpec Consultants.
Yep, which are based up on the south side of Brisbane, doing frequency assigning for all various customers from HF up to VHF.
You will see on one of the slides the work we toward the end of the presentation, the work we do, but some HF, but mostly VHF, UHF land mobile services, base and mobiles, fixed links in both the VHF and UHF bands, plus all microwave fixed links, whether it's 1.5 or 85 gigs, we work with that. We also have at RadSpec the opportunity of providing both path profiles and coverage predictions if you're required.
Right. Now, Russell's slides are starting off with some very basic stuff, so it's probably like going to be elementary to a few of you, but let's just so everyone get an overview of what it's about. He will get into more complicated stuff towards the end. I just ask that we leave all the questions about not related to the particular slide, leave that till afterwards. Only ask questions about that particular slide that's up so that we get the thing going. So anyway, over to Russell.
Okay, first I'd like to say thank you to your executive for inviting me. Thank you to Mark for organising all this. And thank you too, guys, both members and your guests, for coming along to hear what I've got to say. I'm just going to go into these slides. There's about 100 and something of them. Don't panic, they're not all going to be tedious. A little bit about myself. I did my training with DCA as a technician in training. I spent 5 years out of Sydney working in HF RTTY and associated VHF links to control those. In the mid-1970s the PMG broke up and what is now the ACMA was formed. I started working there in frequency assignment, except for 1 year in the mid-1980s where I left the radio industry completely. Went to work in a subsidiary of the John Fairfax organisation and came back into the ACMA and have been doing frequency assignment right through until the time I left the public service in early 2005. That's a bit about me as a hobby. I spend a lot of time working backstage in community theatre. There's a few blank slides to try and break up where we're going to. About the ACMA, this is a fairly brief history and the dates are not altogether correct because finding their timeline is difficult to say the very least. Each department has written its own little glorified where we came from, where we're going. But basically up until the 1975 it was the Postmasters General Department. 1975 the establishment of Telecom Australia and Australia Post as independent semi-autonomous government business enterprises, and what was left over was the radio branch of the PMG. That moved into what is now various iterations of postal and telecommunications, spectrum management agent, communication and the arts communications, and eventually ended up around about, it might be late 2004, early 2005, as the Australian Communications and Media Authority, which it is still today. Their focus is primarily that of policy, and they do very little frequency assignment work. How the frequency assignment work came about, I will make mention to a spectrum license shortly. The ACMA said, well, spectrum license, we'll treat that as a block of land. That's yours, you do what you want with it, we're not interested. So that people had to become accredited to do frequency assignment in that block of land. So they met specific guidelines. It didn't take them long to say, well, if we can do it for these people, we can do it for everybody. At the same time, the public service was trying to downscale its size, so you guys can do it, you guys can do it. That's where RadSpec started up. So I'll just move straight on to the licenses. I've already mentioned the spectrum license. It is seriously beyond this discussion, but if you think of it as real estate, you can develop it, you can subdevelop, you can divide, you can sublet it. It's all those things and more, and very complicated in terms of how they're licensed. As far as we are concerned, it is not RadSpec's core business. Apparatus licenses are what you will see the most of. Your typical base and mobile where you have an apparatus at a location talking to either other vehicles or a fixed point-to-point service. And of course, the third class is the spectrum, the class license, your freebies, your remote controls, CB radios, wireless microphones, all these sorts of things that are so low in power and so random in their distribution. Trying to police them is it's a nightmare. It's just not cost effective. The way the ACMA have set their license up, if the fee falls below a formula below $41 an hour, forget it. Everything bottoms out at $41. Licenses that we're going to talk about today, the apparatus licenses, are issued on they're a means of collecting tax. Start and end of discussion. That's a tax you pay for the frequency of operation, the bandwidth that you're using, the power that you're using, its location, and the purpose. So up on top of Springbrook, you can have all sorts of stuff, your sorts of services, the TV stations, commercial people, they've all got frequency, bandwidth, power, location, and purpose. That's the principles by which the taxes are derived. Complex formulas and pages of sheets, as you might imagine. As Mark said, I'm going to talk in principles, very broad principles, so that if I'm telling you what you already know, please forgive me. If I'm telling you what you don't know, it's not intended to be too complicated. It is just there so we're all coming to each other from the same page. And for analog FM services and analog AM services, this holds true. The emission bandwidth is a simple calculation of twice the maximum modulating frequency plus twice the deviation. And a service that you're familiar with, you have a normal voice communication, your maximum modulating frequency is 3, so twice 3 gives you your 6. Your maximum deviation is 5 kilohertz, twice 5, 10, add them together 16. Simple as that. So on your license you'll see a 16 F3 or something like that. That's how that 16 has been derived. And at this point, the power in the sidebands has fallen to minus 23 dBc. That's about half of 1% of the unmodulated carrier. Now that follows standard Gaussian distributions. Your power falls off and falls away exponentially. But at this minus 23 dB point is where that 16 kilohertz has arrived. So that I'm going to come back to the bandwidth quite a bit, so please keep that in mind. The channel spacing, empirically, now there is no formula for it, hence the empirical statement, that it was 3 times half the emission bandwidth. Well, we've got 16 kilohertz of emission bandwidth, twice that, 3 times half that, I beg your pardon, is 24 kilohertz. For convenience, let's make that 25. Much easier to work out 25, 50, 75, 100 than it is 24, 48. Forget it. And also that provided your 16 kilohertz, 9 kilohertz guide band, your next 16 kilohertz. So you had plenty of frequency separation as well as perhaps geographic separation. The current philosophy, we're in around about the late 1990s, in capital cities particularly, the demand for spectrum was so high that it was a case of, even from RadSpec's perspective, we had to say to the customer, we can't give you a frequency at that location in that band. It just couldn't fit them in according to the current guidelines. So what ACMA did, and they made the decision at the time, we'll simply say, everybody wind your emission down, and that'll leave a bigger guard band. We'll go to 12.5 kilohertz offset, and we'll put in another narrowband service. Right or wrong, and there's good discussions both ways, it's not the purpose of this forum to discuss those. We do have things on 25, 37.5, 50, 62.5 and so on 12.5 kilohertz increments from now on. And how they've arrived at that, exactly the same sort of thing. We don't have 3 kilohertz of maximum modulating frequency anymore, and we certainly don't have 5 kilohertz of deviation. So twice 2.55 is 5.1, twice that is 5, there's your 10.5 on your 12.5 kilohertz channel. So we're on the 16 F3 on 25, we had 9 kilohertz of guard band, we're now stuck with just 2.5 kilohertz of guard band. Okay, the transmitters are much more stable and your filtering is much sharper, but the demand for spectrum has skyrocketed. So we've really still got a problem fitting these things in. An attempt has been made to make the spectrum more efficient by allowing multi-voice channels on a single carrier. Typically 2, but up to 4. It does require extra bandwidth. So if you've got, and some of you may have services or have seen on your licenses, a 25K0 D7W DT emission on a 25 kilohertz channel. Shit guys, that's 25 right out the edge. The next guy butting right up against me there. There is no guard band. So I have to ask you a couple of questions. Let's come to this one first. What does 25K0 D7W DT mean? Okay, we're already starting to get familiar with the 25 kilohertz. Oh, this came about very simply. The ITU, step back again, the International Telecommunications Union is the peak industry body representing all member nations from around the world. The next down is the Australian government. We have our ACMA parliament and things like that. Then we have our band plans, and then we have from there. But the ITU don't make the rules. They make the recommendations. And the reason they don't make rules is because how we apply our law here will differ from how people in Zimbabwe might apply theirs, or how people in Russia might apply theirs compared with Ireland or somewhere like that. So it's up to the individual nations to implement the recommendations of the ITU. Because Europeans, from an Australian perspective, because Europeans have this crazy idea of putting 1001.000, comma, 25 for 1000.25. Hang on, the commas and the full stops are back to front. You and I would put 1,000.25. So in order to overcome this confusion of full stop or comma, they chose to put, wisely, the multiplier, 25 kilohertz with 0 hertz beyond. The next three, D7W, is a combination of AM, FM, 2 or more discrete channels. I mentioned we've got 2 or more discrete channels, up to 4. A combination of information. It could be a bit of data, it could be a bit of telemetry, it could be voice, it might be, God only knows, slow scan TV if they wanted to try it. The last 2 digits are optional, 4 conditional code and time division multiplexing. But I do have another slide that talks about emission designators later, so we'll continue on from there. Yeah, I've just said the big problem is there is no guard band, and the demand on spectrum. You will see in a later slide, ACMA have tried to address this with a series of frequency distance constraints. So if it's co-channel, it's got to be so far away. If it's this far off, it's got to be that far away in distance. I'm not sure that it's the best approach, but it's the one we have to work with, so that's what we do. As I said, you can't help ponder, is this spectrally efficient? I don't know. Another fundamental, we have a single frequency simplex service. Press to talk, the guy at B receives it. Over, the guy at B, press to talk, the guy at A receives it. Single frequency, one direction at a time. 2 frequency simplex is probably what most of you use. You still might use the press to talk, but we now have 1 frequency for the outbound and 1 frequency for the inbound. Sometimes called wrongly duplex, it's truly half duplex. And what we have is full duplex, your mobile phone. You and I can talk to each other over each other at the same time. Better catch up where I'm up to, please excuse me. I was going to flip these pages over as I went, but here we are. I think we're up to them. Okay, when making an assignment, 5 criteria must be met. The channel reuse distance, the adjacent frequency channel separation, the intermodes, there's 5, they're up to 3, the images, and the harmonics. Yep. I'm going to address those 5 in turn now. Before I go on, am I getting ahead of anybody? Is there a question that needs to be answered? Thank you. Okay. Co-channel reuse distance for single frequency high power services. By definition, the ACMA talk about EIRP, the effective isotropic radiated power. Anything above 8.3 watts EIRP is deemed to be high power. Below that is deemed to be low power. They only have that one breakpoint. There's some discussion, some argument about having a second, or perhaps a second breakpoint, but it's still on the books at the moment. So we'll just stick with the high power. All VHF services co-channel, the minimum separation between those two services must be 160 kilometres. If it's UHF bands, because the propagation of the 450 megs doesn't travel quite as well as the 150, they've dropped that reuse distance down to 140. This is still singles frequency services. For low power services, you can see a similar reflection of, you're not going to see the pointer there, 16 kilometres for all VHF services and 10 kilometres for UHF band. Primarily because most single frequency services are handheld to handheld. They're at ostensibly 1.5 metres above the ground. They're not going to be very far before you get trees, buildings and other intrusions. So 10 kilometres co-channel reuse is fairly generous. Two frequency. Yeah, okay. Two frequency services may sound a little bit inefficient spectrally when we talked about the demand on spectrum. You'll see when we come to the intermodes why two frequency spectrum is better than single frequency for our purposes, for radio communications. Across the whole lot has been reduced to 100 kilometres, and for low power services, irrespective of the band, down to 10 kilometres. The second point is the adjacent channel frequency distance constraints. Yes, the ACMA have a series of very awkward, very convoluted lookup tables for this criteria. You'll see an example of one later. Someone's in trouble. Abandon ship, abandon ship, abandon ship. Okay. With regard to these frequency distance separations, loosely it follows a simple exponential decay. If you're really close, 100 kilometres, a little bit further away 90, a little bit further away 80, but by the time you're way out here it's down to 5 or 50 or something like that. So you can see an exponential decay in those. Intermodes I'm going to skip right over because we'll be coming back to that. That's the basis of what we're talking about. The fourth one is images. I was talking with gentleman outside about, yes, exactly. The first radio I built, I was still in primary school, so about 10 or 11, was an AM receiver. We're living in New Guinea. So I understand a lot of what this was, and before I went to school, I understood what an IF was. I was pretty happy with myself about that. Building a radio and making it work straight out of the book, and with the help of the DCA technicians, I've got to be honest. Now, what we have in terms of images, I got off the track, I apologise. Let's say our AM band, for the purposes of this discussion, has a range of 550 kilohertz to 1550, approximately 3 to 1 change. Our oscillator is tuned to change from 1 meg to 2 megs. That's only a range of 2 to 1. The reason they've used high side injection here is that in those days it was really difficult to make an oscillator move very far at all. A 2 to 1 range on the oscillator was about as far as it would move. So if we looking at the set, we got your filter, first RF amplifier, your mixer. The output of the mixer is going to be the two inputs, the sum and the difference. So we have, let's just say, 550 and 1000 coming out of there. We've got 1550 and 450 coming out of there as well. Our filter says, yeah, we'll get rid of everything except for 450. So at that frequency, there's our 450. When our oscillator's up here at 2000, subtract the 1550 from it and we still get 450, and that will mean that this amplifier or that filter and this amplifier can now be very, very tightly tuned to that frequency only, and we know damn well it's going to work. As you get up into the VHF bands and UHF bands, at this point we put another mixer and another oscillator, and for a long, long time the first oscillator was about 10.7 megs, the second oscillator was, guess what, 455 that we use today. And that gave an extra degree of discrimination for your service at these higher frequencies. Some sort of demodulator and audio amplifier. But I want to listen to the 550 station. Somewhere just not too far away but over the hill, someone's got a service on 1450. Subtract that and what do we get? I'm going to hear not only the wanted station very loudly, but some sort of distorted 1450 in the background, because this filter and amplifier doesn't know the difference between that 455 and that 455. They both get through. There's your image, my wanted and my image frequency. And the last of these was harmonics. The way we do the calculations, we simply look at multiples of the proposed transmit frequency may cause interference to nearby receivers. So if you've got a service, and again I'm going to pick easy numbers, operating on 100 megs, its second harmonic is 200. If someone over there has a receiver on 200, they may hear it. And conversely, there's the same service operating on 100. If someone down here's got a transmitter on 50, twice that is 100, so they may have cause to your interference. So a quick look at this table will explain a lot. This is based on 435 with a 16 kilohertz bandwidth, just for purposes of our discussion, numbers that you're vaguely familiar with. Twice 435, 870, but the emission now is doubled in bandwidth as well, because we're multiplying that whole part of the spectrum. Up there we have fixed point-to-point and land mobile services, possible problem. 3 times that, up around the 1300 aeronautical radio nav, so your 435 meg transmitter may cause interference to some aeronautical radio nav, and of course 4 times that puts it up into the microwave services. Your cellular mobile phones used to operate about 1.8 gigs, that's remarkably close, and fixed point-to-point services are starting to make appearances there too. We only ever look for 4 above, and coming down half of that, now the emission bandwidth is, because double that means it fits into my 16 kilohertz, so we only need to be a little bit off frequency, but in that 200 to 220, or your TV stations, the old VHF, channel 9, 8, 10, 11 sort of thing. 145, that's only because we're based at this. You can see that exterior paging may cause a problem, and I have separately some more information on that one for you. 88 to 108 is your FM broadcast services, so these guys, we used to look at them out for these sort of distances, 300 metres, 100 metres, forget it. If this FM broadcasting station is transmitting at 35, 40 kilowatts, that's a lot of filtering going to be needed so that it doesn't interfere with our receiver. So these figures, although they're historically very old, I just took them out of a guideline that we had. They've never been rescinded, but they seem to work. Once you get this far down, they can be co-sided, but again, bear in mind, 20 metres away or on site, a TV station on those channels may have caused grief for you guys. Now, the definition for the order of an intermod product, this is straight out of the book. The product is, the definition of an order of an intermodulation product is the sum of the absolute value of the coefficients. That's not mathematical gobbledygook. You've all seen numbers that look like this. You have a coefficient, a variable, and some exponent. 4x squared. To apply that to this definition, there's my coefficient. If that's 4, it's 4. If it's minus 4, the absolute value still says it's 4, so you ignore the sign. So for our definition of intermods, a second order intermod is 1 plus 1 is 2. not minus 1 plus 1 is 0. No, no, no. Absolute value, 1 plus 1. In many radio applications and in audio applications, it's the odd order intermodes which are the most significant as they fall closest to the original frequency components and therefore closest to our desired signals. I throw in audio there because if any of you do experimenting with audio amplifiers, intermodes in audio amplifiers can be a real problem. So let's validate this. Now this is where I'm using simple numbers so that in your head you can keep up with me. I mean, it would be very easy to put in 146.725, 146.750. Suddenly you're trying to keep track of what I'm doing. This is chosen so that you in your head can see where I'm going. The principles remain the same whether I use 100 and 101 megahertz implied, or if I could strike that and say channel, whether it's a 6 metre or a 20 centimetre, who cares? The numbers and the ratios, it's the ratios that stay the same. So a second order, once A plus once B is 201. Not much problem. Take them away. Don't know too many minus frequencies, guys. Reverse them and add them up. 201. Take them away. Plus 1, yay! So of these, nothing's anywhere near what we've got. It looks like even order harmonics are not a problem. In a tabular form, and all I did was put that in a little spreadsheet and you can see what's happened. A plus B, A minus B plus A minus B, B minus 1. So again, no problem. With that tabular form in mind, let's look at third order intermodes. Adding up, we're up in the 300 whatever, channel, megs, doesn't matter. So from now on, it becomes quite clear that the additive ones are not a problem. They probably exist, but we don't have in our service operating around 100 megs anything that's up to 300, so it's not a problem. The only two that are a really problem are just below and just above. So you'll see most are of no concern. Of those 8 which are mathematically generated, only 2 are close to our existing frequencies, and I've highlighted those in yellow for you. So what we see is that if we had a receiver on either, is that red clear? I'm sorry, I didn't think of this for the distance. 99 or 102, and intermodes were generated, then we'd probably get interference. We note that the intermodes are spaced away from the carriers the same as they are separated from each other. We had 100, 1, 101. Another one takes it to 102, another one takes it to 91. So the intermodes are going to fall on even steps, even multiples of that separation. Yes, it certainly looks like the odd order intermodes are going to be a problem, but it's not that simple, guys. I'm sorry, it's really not that simple. What about the bandwidth? Okay, for this illustration, I'm going to assume that we have a channel bandwidth of 0.1. So you can see easy numbers again. This carrier now goes down to 99.9 up to 100.1. This carrier goes from 101 down to 100.9 and up to 101. Multiplying these out now gets really messy really quickly. You want to sit down and justify all those? Spreadsheets, trust me. Confusing. I've got a can of drink here that I've hardly touched, but thank you very much, Mark, I will. Yeah, you betcha. Would an illustration help? I'm tipping it probably would. There's my carrier. Here's all the calculated intermodes that end, and there's all the calculated intermodes that end with their respective bandwidths. Yep. The third order intermodes occupy up to 3 times that initial channel bandwidth. We've looked at the thirds, we've looked at the fifths, what about sevenths? And again, you'll see a pattern developing. Samey same, Most of those are fictitious or unreal numbers. Most of these are way out of the bandwidth. We have a small group in the middle of our calculations which are a potential problem. And you'll note we spoke before about the separation. 97, 98, 99, our service is on 100, 101, 102, 103, 104. So with third, fifth and seventh order intermodes, we've suddenly taken up, with this example, a lot of spectrum, 7 megs of spectrum. Three below our lowest carrier, 3 above our highest carrier. Putting those in pictorial form, there's our fundamentals. Third order, fifth order, seventh order, with, as you'll see, the growing bandwidths. What I've also tried to show is they do tend to fall off exponentially. So whilst there is a problem, depending on your filtering, these could be down by 20 to maybe 50 dB. And there's also, as we'll learn, conversion losses in the equipment as well. So they do attenuate very quickly, and for many, many years we did not look at seventh order intermodes, and it's still not on the ACMA guidelines to consider them. I will show you at the end of the presentation one example where it was a problem. And in all the years I've been doing assignment, that's the only one I have encountered. I know that Motorola back in the 1980s, late 80s, early 90s had a problem with 1.2, but that was generated on their site with their equipment, so they had to manage it themselves. But generally we do not consider, I say generally, and I'll give you again an example later of where we might. So the comment is that this is a real problem for single frequency services. Transmitters and receivers are close in frequency and distance. I hope you're reading that quicker than I am. It can be separated by going to 2 frequency operation. And all of the following applies. Where do the intermodes occur? Potentially anywhere there's a nonlinear element. Whether it's single frequency or 2 frequency, they might be in the transmitter PA stage, the output filtering, the receiver input filtering, the receiver front end, or something else, something nearby, some nonlinear device nearby. Oftentimes referred to as a rusty bolt syndrome. You've got a tower outside there, and I believe some of the bolts in that were at one time a problem. I believe they've been addressed now. So rusty bolt syndrome does occur. It sounds strange, it sounds a silly name, but think about it. You've got a galvanised iron tower and a steel bolt, and we've got zinc and we've got steel and a bit of moisture and salt, and suddenly it's a nonlinear diode. That'll detect it. It possibly re-radiating with a tower like that. It's a pretty good radiator. They do happen. Anecdotally, one of our field techs in Melbourne said, yeah, we found it on such and such a tower, we fixed it. Out of the back of a truck he gets the biggest sledgehammer he's got. Wallop! Boom! Where's the spectrum analyzer? All gone. That was only a temporary fix, but at least it proves the point. They had a problem on the tower. Right, now the whole purpose of this discussion is to talk about intermodes. So it will be processes only, so that you get a broad understanding whether you're talking HF or 1.3 gigs. The principles will remain the same. Where do intermodes occur? We've already touched on this. It's come out of one transmitter, is radiated to a nearby transmitter. Some buggery happens in there and lobs on this receiver. So it might be caused by A, acting in B, and landing on our receiver. One way. Or it might go from B into A, similar sort of buggery, and back onto our receiver. In this case, not caused by A but by B, acts in not B but A, and still falls on a receiver. That's the second. Third one was logical. Out of my transmitter, out of his transmitter, and onto someone else's receiver. We've still got some sort of non-linearity here, so we've got a problem. There's one more. I mentioned that just a few minutes ago, the rusty bolt. In this case, it could be a bit of a cyclone wire fence. I'm not sure. That's what the graphics came up with, so that's what we got. But anyway, it comes out of a transmitter, mixes, re-radiates somehow something and lobs on a receiver. So just to recap those, there are four basic. From A in B onto the receiver, from B in A on the receiver, the 2 units into the receiver and into something else, which is incalculable. We don't know where that rusty bolt is, or if it's not a rusty bolt, something else. So far we've only looked at 2 station intermodes, A and B. Guys, I've got to tell you, the fun's just beginning. We need more services. So everything that we spoke about for before can now be repeated to include transmitter C. Originally we spoke by A acting B falls on the receiver, it could be C. Or originally we spoke about B acting in A, now it can be C. I'm sure you can see that the problems are going to grow. And there's another problem. All 3 transmitters could be up at one time. And I'll say that because historically, 3 station intermodes were not reckoned to be a problem. The ACMA, and I was working with ACMA in those days, no, we don't worry about 3 station intermodes. Why? Because in those, shall we say pre-2000 for the breakpoint in our discussion, were almost all press-to-talk services. And in those press-to-talk services, you guys know better than most, your communication was very succinct and it was fairly short. And in the commercial world, you know, like taxis, I want an address. 123 Main Street. I want this. Can I? Customer's not here. Please wait. Short conversations. Press to talk, press to talk, press to talk. The statistical probability of have him and her, all 3 of them up at once with that sort of short press to talk was very remote. And if it did happen, it would probably either the leading or trailing edge of their over. That's why ACMA in those early days chose to not consider third. But things change. We'll continue. There are only 3, fortunately, combinations of 3 station third order intermodes. A, B minus C, and the other iterations of it. And we end up with these intermodes. And again, these don't have to be 100 megs. That could be channel 100 in your particular band, channel 101 and 102 in your band. Of course, the same sort of thing if we had another service at 99. You can see this is going to get awfully complicated very quickly. If 1 or 2 of these servers are up continually, every time you get the press to talk, you're going to have a problem. And this is happening. So many SCADA systems, so many data telemetry systems out there monitoring this, talking to that permanently, they're on all the time. No more press to talks, guys. Okay, let's just do a recap. What we've looked at is the ACMA silent criteria. Channel reuse, adjacent channel frequency distance constraints, the intermodes, we've dealt with them a fair bit for you, images and harmonics. Now we'll move on to the mechanics of making that assignment. And again, you'll see assessing intermodes is a major part of that assignment work. First thing the application comes in, what do you do? The processes in RadSpec are that our administration staff will read the application, they'll generate a work slip, put key details on that work slip and pass it through to the techs. Read the application. Now, when I first started frequency assignment in the 1980s, my senior technician at the time, everything he said, read the application. Understand what the customer wants. Have they provided all the information? And I'll give you an example briefly in a minute of where a customer doesn't provide all the information. And have they provided any unique information? That's as important as that. Once we've got a good understanding of what the customer wants, if necessary, liaise with them. Talk to the guys. They know what they want. People like RadSpec and our competitors are, I'd like to say we're pretty smart, but sometimes we don't quite get it right if the customer didn't say what they want. So I'll give you, oh yes, all the information. Some of our customers, they only ever deal with high-rise cranes in the construction industry. It's a unique application of a land mobile system. We've got a base in the tower, we've got the spotter, the dogman and whatever running around down the ground. Sometimes an email from this particular company says, I need another service at 123 Main Street. Sorry guys, that's the entire application. Only because we know who they are, what they do, we can fill in all the blanks that they need. But yes, you have a question.
I was just going to make a comment. One of the in-amateur repeater assignments, one of the common failings that causes immense trouble is antenna definitions. What type of antenna? And an operator goes white stick.
Okay, the antenna is critical, and I will answer that question now.
No, it's a fact.
Actually, if you would indulge me, we can talk about it later because it does come up in another slide. Thank you very much, but antenna is critical. Some of the band plans talk about horizontal loading, some talk about vertical loading, and it's really very simple. Customer one comes along, second customer comes along, give him the next available channel. The third, the fourth, the fifth, we run out of channels, then we go back and start putting them, go back to channel 1, 2, 3 and so on. The alternate is vertical loading. Put everybody on channel 1. Put the next guy on, frequency, distance, constraints, other parameters, all fit in, put him on channel 1. Oh God, we can't put any more on channel 1 at this location, so then we move to channel 2. So we have either horizontally or vertically loaded. There are good discussions in favour, and there are equally good discussions against each of these formats. From a practitioner of someone else's policy perspective, if the guidelines say horizontally load, that's what RadSpec do. If they say vertically load, that's what we do. And I'm sure you remember these. I'm repeating them. That's the processes we need. Co-channel, adjacent channel, intermodes, images, harmonics. I'm going to look at, for a start, the first two. They go hand in glove. This is an extract from a report, a copy of which I have here. We interrogate the database. In this instance, it was based on your 2-metre services. These in blue are channel markers with a distance set at 0. These columns are, that's just a channel number, and that might not be the right number. I fabricated these to make the example for you. So if 147 neat is not channel 16, please forgive me. But for the illustration, it shows what I'm looking at. The next column shows that service is 140 kilometres away, that one's 91, that one's 86, that one's 69, these are over 100. So the red ones, because they are local, they're high power services, you can see 120 watts, 120, remember, 8.3 watts CIRP, so they're all high power services, they're all closer than 100 kilometres, I can't use those. So now I'm looking at my channel reuse distance, and I'm also now looking at the frequency distance constraints, because for these tables, something that's 25 kilohertz away, I think is down to about, I stand corrected without looking at the tables, I think it's about 2 kilometres. You can have a 25 kilohertz channel separated from yours 25 kilohertz away, down to about 2 kilometres away. I'm trying to scratch my mind, but what it's telling me, they well, and even though they're high power services, I'm not using this channel. It's certainly outside that frequency distance reuse. That full table is available. I've got it here for you. The last three, I'll treat those together because the way the software packages it, It just does the calculation, does the report, all on one page for you. Let's look at a specific example. We need the centre of the service. ACMA specify 10 metres. If it's less than 10 metres, ACMA deem it to be co-sited. So if you've got a tower out the back there and another one in this corner of the building and it's only 8 metres apart, guys, I suggest you on paper move it around the corner so it's 10 metres apart at least on paper. And if the inspector comes out and says, oh yeah, fucking around the corner, that'll probably be 10 metres, tick, you'd be right. Okay, so you have tower 1 at this address at 85 and tower 2 at 85 and the guys be happy. But if you can see they were only like, guys, they're only 4 metres apart, come on, they're not different addresses. So that's ACMA philosophy, and it makes sense when you come to do further calculations. The adjacent service listing has a radius of, in rural areas, 3,000 metres, and in urban, with caution, 1,000 metres. And I say that with caution. If I were doing something in Mount Cootha or downtown Sydney or elsewhere in high spectrum demand areas, even with a adjacent service listing of under 1,000 metres, you'll come up with hundreds, and I mean hundreds of services. So with caution, you can also say, I can cut that radius down a bit more, expecting that everybody's got some pretty savage filtering on their equipment. I know it's going to pass. But again, the software allows us to look at those things. And the frequency range is limited to typically 5 megs below the lowest operating frequency. If I went back to that slide, we're talking about 100 and... Move on to the next slide because it answers the question. A site that some of you know, the Vertel Sprite at Springbrook. I've shortened these. The way they're recorded to 6 decimal places of your coordinates, I beg your pardon. That's accurate to 10 metres. Take it out to 6 decimal places and you're accurate to 100 millimetres. Why ACMA have that? God only knows. Anyway, that's what we're stuck with. That works. In old days, degrees, minutes and seconds, if you took it down to tenths of a second, you're talking accuracy of about 2.5 metres. We're talking rural, 3,000 metre service range. If we were doing a check in the 2 metre band, 5 megs below the lowest in that band takes it down there, 5 megs above the highest takes it up to there. Likewise for your 70 centimetre band. That's the ASL. So based on those coordinates with that radius, with this frequency range. So you end up like a slice of pie. There's the centre, it's that far around and that thick. Do the intermod run. Now this is where the software really pays its dividend. Remember those drawings? We had transmitter A, transmitter B, cores on the receiver. So the software then, massive 4 next loops. The proposed transmitter is treated as the caused by. Every existing transmitter is treated as the acts in, and it looks at all receivers, existing and proposed, for a falls on. The software reports any hits and the calculated levels. The second part of that run, we've done that big 4 next loop. Now what we'll do is swap these over. So now the proposed transmitter is the acts in. All of the above applies. All those existing services are now cores act in that, falls on a receiver, and it lists the hits for those. And the third part, from both into the receiver, it gives you the hits for those and the levels. That's a typical sort of report from some old software. The definition in these was transmitter outer. If I have 2 transmitters and receiver, that's the outer because it's further away from the receiver. That's the inner because it's closer to the receiver. Just a physical separation in terms of numbers. But these services, there's only 300 kilohertz difference with the transmitter onto that receiver. Comes up with the distances between the transmitter and transmitter to the inner receiver and the receiver to the outer transmitter, and it calculates the levels. So this is taking into account the path attenuation, those conversion losses, the path attenuation and the received level, and it's come up with some apparently wacky numbers. The receiver sensitivity is typically minus 149 dBW. These are all in dBW. So that one's pretty much right on the threshold, that one's way below. The software, when it was written, didn't exponent to below the noise floor. In fact, I've seen these with like 700 and 800 dBW, you know, it's just not going to happen. But what I'm telling you here is we do have a potential problem for intermodes to occur if I propose to put that transmitter and receiver up at that Springbrook site. There is a real potential for interference there. The next part of that run, we'll look at the intermodes, the images, I beg your pardon, images. We spoke earlier about 10.7 and 455. If any appear, right, there wasn't any there, it would produce those, but it doesn't do any calculating levels, it just makes you aware of them. And the last thing it does is list of all those, the harmonics of the transmitter going up to the 4th, the subharmonics of the receiver coming down to the 10th. We looked at some of those before. If we find anything, we advise the applicant as or when necessary. And it has been an occasion, especially where it's relatively near a FM broadcast service. The 4th harmonic of 100 point something is going to fall on a 400 point something service. So there is a problem. You just let them know. They can say, yep, we can put a notch in and filter that out, or if it doesn't occur, we won't worry about it. But at least they know. They know if they do get a problem, we're about to start looking. Now, also, I bring this to your attention, as you see, when making assignments for user-specific bands, endorsements from the peak industry body must attach those submissions when we make them to the ACA. In your case, I believe this has changed, but it certainly up until about at least the beginning of this year, the Wireless Institute of Australia. So we've done all the calculations for you. Peter Mill, that you might know from radio electronics development in Victoria Police, is the, or was the appointed delegate. All those submissions that are made on behalf of the amateur fraternity, squirt them down to Peter, he has a look at them, say yes, they fit within the band plan, and when we get the endorsement from him, we then send that, he sends that back to us, and we attach that endorsement to our submission to the ACMA. They say yes, oh hang on, this is an amateur band, yep, the WIA endorse it, that's okay. And it's not just you guys, we do assignments for the rail industry, so the Australasian Railway Association have to endorse that assignment. We do assignments for government departments, the National Consultative Committee on Government Radio Communications, Queensland, have to endorse theirs too. So what it's telling the ACMA, not our problem. The WIA said it's okay, we'll tick the box. Sorry, I missed that sarcasm. Now I'm sure you guys have got a problem with paging services up at Springbrook. Yep. It was on that special request that I'm going to give a fair bit of background to what, how, why, and I hope not the positive answer, but you'll get some guide. That's what I'm hoping. I believe it's 146.7 that's causing part of this problem. It's currently licensed on the ACMA database as an F2D with 120 watt transmitter power. It doesn't give on the license it doesn't give you the system loss, but it does specify the antenna gain, and this is coming back to touch on what you were talking about a minute ago. And it does give the EIRP of 400 watts. I've worked backwards and fitted that in as assumed, and it's a realistic figure. That particular frequency is paired with 146.1. 2.3 kilometres away there's two VHF paging services, and they are licensed, not unlike yours. 16K0 F2D, that should be a capital K, Russell. Transmitter power 100 watt, 0 dB loss assumed, 5.2, and it's licensed there. Do you remember earlier on that the intermodes were multiples of the separation? between the transmitters. Those two transmitters are 75 kilohertz apart. So if I take off 75 kilohertz, take off twice 75, take off 3 times 75, that's still a bloody long way from 146.7. Maybe we got some amateur services on site. Yep, we got 2. That's transmitting 50 watts 83, that's transmitting 25 83. Let's have a look. I ran some separate software. All those services on site, not an intermod to be seen. This particular software, if there's no intermods, doesn't even produce result none found. It just leaves the page blank. So hark back, remember those two paging services were licensed with a 100 watt transmitter. What's wrong with that? If I apply the sums, 5.2 dB up on that's only about 320, 330. Now we know the paging services are high power. How about we change our 100 transmitter to 950 watt transmitter? We'll insert 8 dB of system losses made up of cable and connectors, 3 cavity filters, a surge protector, and 30 meters of cable. The resultant EIRP is now calculable to 500 watts. There was a time when that was permitted to be 1,000 watts. But all the licenses now are 500 watts. So what I've said is that if the paging company was to put in those 3 transmitters, 2 band pass and 1 band stop, that would be the output of the transmitter noise. A typical Gaussian distribution, you'll hear it and see it so often. But when we put those 2 band pass filters in and the band stop tuned appropriately, what have we got? Relative to the carrier, -3, down here at -50. We've got 47 dB of rejection just by proper filtering at the paging services. The problem is it's very expensive, tedious to set up and tedious to maintain. That was a theoretical one. Now let's be practical about this, guys. We're not 100 watts, but 450. We've got 4.6 dB losses, cable, 1 filter? Yeah, that's about right. 5.2, comes out at 500 watts. So that could be what's installed up there that realistically makes them compliant. That's just being practical about it. Just ignore the band reject filter, but you saw the product of that. Just take into account if they've got that single band pass filter, that's all you're going to get rejection. As an aside, 2 megs, because they're talking about 148, your guys' problem is at 146 point something or other. That 2 meg separation, and I think it's less, is only about 1.4% of the difference in frequency. 1.4% of the difference in frequency is putting that attenuation only 15 to 20 dB down on their carrier. But they put the filter in and they can walk away hand on heart, yeah, we put filtering in. So we've got some filtering. Let's assume it is radiating 500 watts. We've come up with a couple of ways we can justify that. Free space path attenuation is a nice easy way to calculate these. For most services, an empirical value is free space plus 10 dB. Now if you're doing base mobile configurations, there's a couple of variations of a guy called Hatter. A Hatter model has one for urban clutter and one for suburban clutter. But you know what, when you start analysing them over the distances that we're talking about, free space plus 10 dB is, yeah, it's pretty close, mate. And for fixed links, Longley-Rice models, slightly different numbers because high site to high site and very little terrain interference. So there are differences, but for our purposes I have chosen to use free space. Why? Because that's a tower up there, that's a tower there, and it's direct line of sight and there's stuff all different. You're not going to get very much other than that free space attenuation between them. So whilst academically it might be wrong, from a simple illustrative effect it's going to be near enough for what we need to know. Formula 32.4 plus 10 log the frequency in megs plus 20 log the frequency in megs plus 20 log the frequency in the distance in kilometres. Insert the numbers and we come up with 83 dB of attenuation from over there, 146 megs, 148 megs to here. 83 dB attenuation, that's a pretty lot. What's the problem? Well, let's look at that. There's my initial start. We know that 10 dB is 10 times the power. There's another 10 dB, there's another 10 dB. Right, 83 dB. That's pretty low power. Hang on. The receiver sensitivity is 1/4 of a microvolt across 50 ohms. That's shit. It's still 86 dB below that. So that transmitter power, all that attenuation, is still 86 dB potentially above our receiver. But the good news is they put in some filtering and we put in some filtering, and now we're still 46 dB above our receiver threshold. Maybe we are experiencing some interference, some intermod interference. 46 dB above the receiver threshold at that site. In an ideal world, you'd fix the cause. You go and tell the guys up at the, you guys better put some better filtering in, you're causing interference to us. In an ideal world, fix it yourself, guys. You're the amateurs, you're the experimenters, you know all about this shit. Okay, so I'm not giving you the answer here. What I'm saying is this may be a help. It may be a help. A possible solution to the interference in the paging services might be to fit a 1/4 wave stub in the feed line as close to that victim transmitter as you can. It's common sense, but be sure to follow the design rules, because if you don't take into account the velocity constant in the coax and you trim it to this and it doesn't work, you haven't followed the design rules properly. Because you've got to take into account the insertion loss, the coupling joints, and how far it is from that point there to the end of the... Just follow the guides. Anyway, 1/4 stubs, they're great. I really like them. They have almost zero insertion losses at all frequencies except the design frequency. Then it's like back up and across. They are really, really good. Very, very much closely approximate a parallel T network. And at RF, these 140 meg services, you're looking at about probably comfortably 40 to 46 dB, maybe as much as 55, 60 dB of insertion loss over probably as little as 5 kilohertz of bandwidth. It's really good if you can look at them, worth a try. I mean, I'm not making any promises, but it might just help you get over it. Anyway, we only had to recover 40 odd dB, remember, when we looked at it before? Getting close to the end. Emission designators, we did talk about them earlier. We spoke about how the ITU prescribed these things. The full definition of emission comprises of 9 alphanumeric characters, the first 7 being mandatory and the last 2 are optional. The salient features are that the first 4 digits always divide the necessary bandwidth and can be in the range of 0.001 of a hertz to 999 gigahertz, just for the necessary bandwidth. That's a pretty widespread. Most of what we're going to cover will fall in there. Next 3 symbols, and again we've touched on these, provide details of the basic characteristics of the emission. And the last 2 symbols, which are optional, describe any additional characteristics which may be useful in providing a more complete picture of the emission. So we looked at 25K0, let's look at the 16K0, a standard analog voice channel. We understand how we've arrived at the 16 kilohertz. So we've got our 16 kilohertz of necessary bandwidth. F tells its frequency modulation. 3 is a single channel containing analog information, and E is a telephony including sound broadcasting. So that's what we've got, a single analog voice channel. The last 2 digits are optional, and in this case I would be J for sound of commercial quality and no multiplexing. It's easy to see why in some cases these are optional. as in this case, Jn, tell us nothing about this emission that we don't already know. But on the 25K0 D7W dt, that dt did tell us, the t told us it was time division multiplexing. So it does give you a bit more of an information on what's happening. Where are we up to? In the 1980s, probably some of you may have rolled your own. You built your transmitters, built your receivers. The equipment specification for commercial equipment, the stability was quoted as 50 parts per million. So at 435, 50 parts per million means that that service could drift down to there and still be in spec. It could drift up to there and still be in spec. Likewise, 25 kilohertz away, this dude could drift down to there and still be in spec, or up to there and still be in spec. But that was the equipment specification in the 1980s, 50 parts per million. Today we talk in absolute values. We have made assignments at 412.471875, down to whole hertz of resolution, with an emission bandwidth of our designator 4K00 D7W. 4 kilohertz of bandwidth, some sort of digital multi-condition code, cases as above. So long gone are the days where anywhere within that 50 kilohertz will be good enough, mate. If it's not on frequency, chances are you're going to get interference by somebody else. Now, I'm going to come back to these intermodes. I originally built this little excerpt from a spreadsheet for passive repeaters in microwave links, which works for passive repeaters in UHF links too. What I needed to do was work out the path attenuation between the transmitter and the repeater, and from the repeater into the ultimate receiver. Passive repeaters are just that. I want a fixed link between point A and point B, but point B is on the, well, if you guys are up there trying to turn, and my bloody service is down here and it's all shielded by Melbourne CBD or something like that, I can't hear. So they end up putting, and this is a microwave service, back-to-back dishes on the top of a tall building. It can see you guys out there, terrific. And we'll squirt it down the end here. So all it did was it just picked up the receiver and re-radiated it back down the side of the building. So that short path was about 100 metres long, and it really was. 35 kilometres out to Glen Waverley and 100 metres down the end here. But it worked a treat because you could now get your service around the corner. But we needed to know the re-radiation level so we could calculate. So this spreadsheet evolved. And it didn't take long to verify when we were developing some of the software, which we did develop, to realise that this could be modified to do what we want. So this might be a typical situation where some of you guys out here in the suburbs, someone operating on this particular frequency, and again these are just numbers to make it easy to work out. 434.9 has a transmitter power, suitable losses, a suitable antenna gain, meets the ACMA criteria of 83 watts EIRP. The path length is only 1.2 kilometres, suburban stuff. The pass loss is free space plus 10, comes up with that. The receive aerial at this customer has a similar sort of aerial. The conversion losses are 12 dB for third order. Again, that comes without. From a lookup up here, if I say third or fifth or passive repeater, these conversion losses change. That's the spreadsheet's written that way. So that re-radiated signal does the same sort of thing and goes from 2.1 kilometres to this receiver, and it falls at a level of minus 181.6. Well, we know the receiver has quarter microvolt across 50 ohms, so it's minus 149. We know the threshold of the noise floor is about minus 160 dBW. 21 dB below the noise, not a problem. You guys can cohabit. That's only 1.2 kilometres, 2.1 kilometres. What happens? We'll move them up to a communal site. And now we've only got 150 metres between one transmitter, the other, and the 100 metres to the receiver. That's possible. 3 towers, 150, 100 metres. All the calculations remain the same, except we now have a receive level of minus 137. A microvolt. It's 12 dB above the threshold, so it's going to work. Above the noise, doesn't matter. We've only got one tower. And we'll whack all the services on that one tower. Duh. Minus 13 dBW. That's 1.5 volts into your receiver. Just because we move them from 1.5 to 2 kilometres to 150 metres to Koto, where that small separation, you can see these problem of distances is going to make a huge difference. We had a policy, do not assign co-sighted third order intermodes. They're just bloody impossible to engineer out for a long, long time. If that was a problem, I'd be getting back to you guys saying, you know what? Don't think you're having that frequency, guys. This is what we found. It's going to cause problems. I'm pretty close to the end. I told you I was going to show you a couple of unusual ones. This happened up at Mount Archer on the north coast, Capricorn Communications, on April 2015. The guy rings me up. So I got a problem. His services are legitimate 487, 482 transmit receive. Somebody else 489, 484. Look at that. 4A and 3B 484050. Bugger, a direct hit. But look at the difference. 3.5, 4 megs, 5 megs separation. It happened. Now I take my hat off to some of you guys, the field technicians, that you go out there and find that. It's easy. I can work out the mass. No problem. You got a problem. But to go out and find that guy, I say I take my hat off to him. But that's the only time I've ever struck it in my assignment career. It happens. The other one is a lot different. It's a 2-station third order, but again, get real, look at the frequency difference. Transmitter A 486, transmitter B 164, receiver 158. A minus 2B is 158. Now, I've qualified that especially at mines. The reason I qualify that at mines have a unique, absolutely unique communication system. Unlike almost everything else, it's above ground. You got, except for the communal site, finite distance between transmitter and receiver. In mines they use what is called a bidirectional amplifier leaky feeder system. Leaky feeders, imagine the old soaker garden hose. Whack your hose on the end and all the way down the hose the water squirts out pretty evenly along the whole length. In RF, if you imagine a leaky feeder doing that, added to it, that's your transverse loss, you've got a longitudinal loss, it's going to attenuate. So although it's spreading out here, by the time it gets down there, it's not spreading out too much. So we put an amplifier in and put it up and it gets down there. We put another amplifier in all the way down the mine. It goes out on about 150, 153, but the guy down in the mine is transmitting, actually goes down the mine 170, back up at 150. You need about 20 meg separation between the two. So these bidirectional amplifiers are filter, amplifier, filter, out. Same line in, filter, amplifier, filter, out. So that's one box, 2 amplifiers connected to the same bit of cable. The filtering says 170 can go down the line, 150 can come back. In that mine, I've got my bloody big piece of machinery, my truck, whatever, my dumpster, but it's only 6 metres to the top of the tunnel, and that leaky feeder's all the way down there. Every service is within 3 or 4 metres of the area on my plant. This is going to be a problem, guys, and it has happened. Because most of the leaky feeder systems work in these sorts of ranges, but they also have UHF comms as well. And I think we've spoken briefly about RAD spec. We're coming right to the end, I promise you guys. It was established in 96 as a result of the ACMA diverging some of their skills we've spoken about. One of them, our current office manager, still works there, and I joined in 2006. So between Narelle and myself, we've got a fair corporate knowledge of the ACMA, which I would say is probably better than most people who now work in ACMA, because you ring up people. I'm sorry, but you ring up those people and, oh, I've only been here for 3 years. I've been here a long time. I've been here 5 years now. Shit, I've been out of it for 15 years, guy. I know what you're supposed to do. Yeah, we're a member of the Australian Radio Communications Industry Association. The services we provide, this is a bit of a plug. I mentioned some HF, not often, VHF and UHF land mobile services. They provide the bulk of our day-to-day work, for sure. We also do fixed point-to-point links in VHF, UHF bands and microwave bands. And again, they provide a fair bit of work that we do. We also do coverage predictions, which is essentially a multi-radial path plot. Now the path plot is from A to B, and it looks at the terrain in between. The coverage prediction looks from our transmitter on that radial. What's the signal strength? Behind the hill. We can hear it again. And it does this about every 3 or 4 degrees all the way around. So you end up with this coloured pattern of where you're going to get good and not so good and bloody impossible communications. That's your coverage prediction. So guys, that's pretty much RadSpec for you. And thanks, guys. Now, I do thank you for your time. I've got one really small presentation that's at Mark's suggestion. You've seen quite a few of the screenshots, but if you want to, I'll run it through. It's only going to be a few seconds. It just say, here's the screenshot capture. I tick that, I click that, I do this, and there's the output. But if you want that, I can run that one for you too. Otherwise, I'm happy to close the books for you guys. 3 to 5 minutes. It's really very short.
Yes, please. Yep.
Some people seem to think that's how you do frequency assignments. No, not so, guys. This is each day the ACMA provide people such as RadSpec an update on the data. So if I'm working today, the data is going to be no older than as of about 3 a.m. this morning. This is a purpose-driven written front end to a database service. I'm going to choose this module to look for the frequencies within 200 kilometres of us, and I have to set up some parameters. A familiar site to you, the lower and upper limit. We're going to try and check out these two channels, and we're going to and that's optional. This is from the lookup table, and I have to custom build the report that it's going to produce. That's the report. In an earlier slide, you probably might remember seeing that much. All it tells us is the frequency. As I said, I made those channel numbers up to make this work. So we've got the markers, the frequency, and all the services on that frequency within that 200 kilometres. It's transmitter power and the coverage. It's in a low density area. When it was assigned, blah, 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 blah. Who owns it, what the license number is, what the client number is, and who that client is. So that's the report that comes out of that bit of the software. And as you saw, it was very helpful to work out co-channel and adjacent services. Now there might be, we spoke about, the assignment criteria might be, we'll vertically load, we'll start at channel 1. Can't use that, can't use that, can't use that, can't use that. Oh, there's a co-sided server. Okay, that might be a possibility, and we'd start doing that. So that's one of the reports that come out. And I told you they ACMA have this hugely convoluted, fiercely complex system of frequency distance constraints. This is Table 6, Part 1, 2, 3. Okay. We're going to look at this part. For this service, we're talking about 2 frequency services with a proposed 25 kilohertz from the existing. Now, I've got that 25 one was greater than or equal to 25 kilohertz, and the existing, okay, it could have been 2 kilometres, 0, I think I was saying 2 to you guys before. I can actually co-cite that one, but if the emission was 6.25 kilohertz, then I'd have to be 100 kilohertz. You can see what I mean. It's bloody complex to try and drive these tables for both the VHF and mid and high bands. That's only the VHF ones that we're looking at. A different set of tables exists for the UHF ones as well. Complicated. Now, I'm going to do a scan. We looked at this first. We decided on that channel. We're going to do a scan frequency. We come up with something that looks like that. And you'll probably be vaguely familiar with this. It's just a report that tells us in frequency order, the distance, who the customer is, the site name. These reports are available. If you wanted one tomorrow, give us a ring. I can just print one out and send it off to you. They email easily. Again, you saw this from a different package of software. I use it a lot when we're doing assignments in mines because of this potential to develop third and fifth order intermodes. This software assumes everything is co-sited. I don't have to put in coordinates or distances. It's just to put in frequency bandwidth and it's done. Love it for that reason. But when we add in this fictitious customer, bugger me dead, it produces some intermodes. So these are just screenshots so you get a savvy on how we're getting where we're going to. Now, using an older database, but the same sort of process, I'm going to do that adjacent service listing and it gets exported off to wherever it wants to do. This is how I can do my intermode calculations. Now, if that looks like DOS-based software, yay, I co-wrote this in 1980 something or other. So all of these screens are partly my work. We are going to print out those ASLs that we had there, and it prints out in a slightly different format because it's older software, but that's the same as what the new one does, but in a different format. Having printed the ASL, we'll go back up and we'll run the calculations themselves. And what I have to do is tell it, oh, these are a couple of variables. We're going to take it off. No, I'm not going to include any third order intermodes. By the way this was written, if I so, let's say I had 3 or 4 channels, I didn't want to add them all to the adjacents, pressing option 4 will change that to will not. So I'll do the calculations for channel 1. I'll do all the calculations for channel 2. But if leaving it there, it'll do the calculation for channel 1 and channel 2 against all the others. Just a bit of a nicety in that software. Press the enter. So I go off, I enter the 2 frequencies that we suppose transmit and receive, and again, because we're a bit bloody done with talking, oh damn, it should have been 147, not 147.6. EE. Go back and the counter then just resets and you make your corrections. This is DOS, remember, it's DOS, not bloody click and change. Now we've set the system up. This was written back in the days when there was nothing like 12.5 or anything like that, so 25 kilohertz, that was your standard tolerance. And again, the way it was written, select a number and these would toggle across so you could change from 10.7 for your first IF to 11.2, 21, or prescribe another. Over that frequency range with a standard of 1 cavity. Press enter and away it goes. There's the output. Springbrook, between those parameters, typical sort of report. You'll see no third order intermodes calculated, 1 isolated, 1 cavity, no isolate. And again, we saw this extracted earlier. It looks at a bit of the transmitter noise and it also gives us those transmit harmonics or receive subharmonics. That's the software that it does. I went back and I changed that module from no to yes. We are going to look for 3 station intermodes, and I told you it doesn't calculate the levels, it just reports them. And look, we've got these ones that we found before. So they're there. So in this instance, my choice of 147 for a base transmit, 147.6 for a base receive is no good. I'm going to create all sorts of buggery on your hill and you don't want me to do that. So I have two options: find another frequency pair, or liaise with the customer, redefine it. If the request had come in and said, I want that frequency pair, then I'll be getting back to you saying, you know what, this is the problem. And he'd probably, damn, I've already bought the equipment, it's coming in from China, I've got to get... So we have a problem. That's what it's all about. And no, it's not as simple as throwing darts at the board, guys. Thank you very much.